This video is all about the inverse Laplace transform. Remember that what we're trying to do here is to find the solution, that is, the output in the time domain, for any system given an input also in the time domain. In other words, if we have a system that is receiving an input like a step input or an impulse input or something like that, we want to find an equation in time that shows the response as a first order response, or as a second order underdamped response, or a second order overdamped response, and so forth. We want to find the equation in time that describes this particular response. If we can do that, we don't have to rely on simulations to know how the system will respond. We can find how the system will actually respond. And we can find the system's response to any kind of an input, not just a step or a ramp or an impulse. We learned in previous videos that the way to find this equation that describes the response is to first find the transfer function. Then multiply the transfer function by the Laplace transform of the input that we want to apply. For example, if we want to apply a unit step input, we would multiply the transfer function by 1 over s. Or if we want to apply a unit ramp input, we would multiply this by 1 over s squared, and so forth. Then we would take the inverse Laplace of this whole thing, and that will tell us the equation that describes the response in time. So today I'm going to be walking you through how to do inverse Laplace transforms. In order to do inverse Laplace transforms, there really are 3 different tools that you need to know, or 3 different pieces of information. The first thing you need to know is you have to have a Laplace transform table. Just like we used the Laplace transform table to do Laplace transforms in the previous videos, we can also use the Laplace transform table in reverse to do inverse Laplace transforms. The second thing that you need to know is you need to know the Laplace transform properties. The properties that apply to the Laplace transform are the same as the properties that apply to the inverse Laplace transform. As a reminder, here are the 2 properties that you need to be aware of. This time I'll write them not as Laplace transform properties, but as inverse Laplace transform properties. The symbol for an inverse Laplace transform is the cursive L with a -1 superscript. The inverse Laplace of any kind of a constant times a function is equal to that constant times the time domain version of that function. The second property that you need to know is that the inverse Laplace of one function plus or minus another function is equal to the time domain of the first function plus or minus the time domain of the second function. These are the same 2 properties that we learned in the Laplace transform, and they apply also to the inverse Laplace. The third thing that you need to know is a bunch of algebra. Sometimes the function that you're trying to take the inverse Laplace transform of does not fit into a specific line on the Laplace transform table, and it doesn't fit into one of these properties. But if you rearrange the function a little bit, then it does fit one of the lines on the Laplace transform table, or it does match with one of the properties. This ability to rearrange an equation until it matches something that you can take the inverse Laplace transform of takes a little bit of practice. In this video, I'm going to show you some examples where we're using each of these three skills, either alone or in combination with other of the skills, in order to find the inverse Laplace transform of a function. I'm going to start with some easy examples where we only need to use one or maybe two of these skills, and I'll end up with a more difficult example that requires us to use some algebra as well as using the properties and the Laplace transform table all together. In this first set of examples, I'm going to show you some problems where all we need to use is the Laplace transform table to do the problem. Here's example 1. We want to take the inverse Laplace of the function 1 over s. We're going to assume in all of these examples that what we're taking the inverse Laplace of is a transfer function multiplied by the input. So here in this example, we want to take the inverse Laplace of 1 over s. All we have to do here is look at our Laplace transform table. In fact, this is the first step of doing an inverse Laplace transform for any kind of a function. The first thing you want to do is look at a Laplace transform table and see if your function matches something on this table. When we look at this table, we see that our function does actually match exactly one of the lines. 1 over s in this table is the Laplace transform of a unit step, or the number 1. So here, the inverse Laplace of 1 over s is just the number 1. For this second example, let's take the inverse Laplace of the function 1 over s plus bk. Here, b and k are constants, and s is our variable. So we want to look at the Laplace transforms table and see if this function matches anything on the table. As we look through this table, we can see that our function matches line 6. In this Laplace transform table, anything that's not s is assumed to be a constant. In our function, we have 1 over s plus bk, where bk is a constant. So we can see that the inverse Laplace of this function here is e to the minus at. I'll zoom in a little bit here so you can see this a little bit better. 1 over s plus a has the inverse Laplace transform e to the minus at. So here, the inverse Laplace of our function will be e to the minus b times k times t. Let's look at another example. This time we want to take the inverse Laplace transform of the function omega n over s squared plus omega n squared. Let's take a look at our table. We're going to always start by looking at the denominator. Our denominator in this example is s squared plus omega n, which again is a constant, squared. At first glance, it might look like this is a match here on line 7. But you know, because of your algebra skills, that if we would multiply this denominator out, it would not be s squared plus a squared. It would be s squared plus 2as plus a squared. So this does not match our problem. We'll keep scrolling through the list. Here we have a line that matches our problem. It is a constant over s squared plus a constant squared. The fact that our constant is omega n and the constant in this equation is omega doesn't matter. We could have something like k times L instead of omega, and it would still match this equation. As long as the thing that we have in the numerator and squared in the denominator are both constants, and they're the same constant, it will match this function. So we can look at the time domain inverse Laplace transform of this, and we see that that is sine times the constant times t. So the inverse Laplace in our example is sine omega n, I'll use our constant, times time. Let's look at one more example where all we have to do is use the Laplace transform table. In this example, we're going to try and find the inverse Laplace of the function s over s squared plus k over m. When we try to match our function to a function in the table, we're going to always start by looking at the denominator. If we look at the denominator, it looks at first like line 10 will be a match. It would be a match in the case where omega was equal to the square root of k over m, or in other words, omega squared is equal to our constant, k over m. However, before we decide that the line of the table is a match, we also have to check to see if the numerator matches. In this case, line 10 does not match our function because we have an s in the numerator and line 10 does not have an s in the numerator. Instead, our function matches line 11 on the table. We have an s in the numerator and an s squared in the denominator, just like this line. And we have a constant here in the place of omega squared. So this line 11 is a match for our function. When we match our function to line 11, we see that our value k over m is equal to omega squared here. So we'll take cosine omega t and we'll make sure and plug in omega, which would be the square root of k over m. And here we have the inverse Laplace of our function. Now, let's look at some other examples where we have to use not only the Laplace transform table, but also some of the Laplace transform properties in order to solve the problem. For this first example, let's find the inverse Laplace of the function L, that will represent inductance, over S. The first thing we're going to do is look at our Laplace transform table and see if our function matches something on the table. Since we start by looking at the denominator, we would see that line 2 appears to match here. However, line 2 matches only as long as the numerator is the number 1. In our problem, the numerator is not 1, it's a constant L for inductance. However, we can then apply one of the Laplace transform properties in order to get our function to match this one in line 2. We can change this problem like this. Now we can apply the property that says that we can simply pull out a constant in a Laplace transform. So we can pull out the constant L and then take the inverse Laplace of 1 over s, which is the number 1. So the answer here is just the constant L. Let's look at another example. In this example, we're going to try to find the inverse Laplace of the function CR over s squared plus LC. Here, C will represent capacitance, R will represent resistance, and L will represent inductance. So all of these values, C, R, and L, are constants. Let's go to the Laplace transform table and see if we can find a match. We'll start by looking for a match for the denominator. Here we have a match for the denominator in line 10 of the table. S squared plus a constant squared could easily match what we have in the denominator. Next, we have to see if the numerator matches. In line 10, the numerator is also a constant. It doesn't have any s values in it. So it looks like this will match our function. However, in line 10 of the table, the numerator is equal to the square root of the constant that's in the denominator. In our problem, the numerator is not the square root of the constant. However, could we make it so that the numerator is the square root of the denominator? I'm going to rewrite this problem by pulling a constant out front and making this function match the form in the table. If we had a function like this, it would match the form in the table. And when we do the inverse Laplace, it would be easy. We would pull out the constant, and then we would go to the table and use the inverse Laplace transform of this standard form, where omega is the square root of LC. So what is the value of A in this answer? In order to figure that out, I have to make sure that this function that I have in parentheses matches the original function that I started with. I need to solve this for A. So my final answer looks like this. All we had to do to find this answer was to recognize what line of the table matches the original function we started with, and then apply the Laplace transform property that says that we can pull a constant out front. However, it took a little bit of massaging the function to figure out what that constant would be. Let's do another example. In this example, we're going to try and find the inverse Laplace transform of this function here. Once again, we'll start by looking at the Laplace transform table and try to find a line that matches our denominator first, and then see if there's one that matches both the denominator and the numerator. When we try to match the denominator, we see that both lines 10 and 11 could match our function. However, neither one of these two rows matches our numerator. In our numerator, we have both an s and a constant. So the next thing we want to do is see if we can apply one of our Laplace properties in order to get our function to match one of these two rows. Remember that the two properties we have at our disposal are the constant property that says we can pull a constant out front, and the addition and subtraction property that says that the Laplace transform of the sum of two functions is equal to the sum of the Laplace transform of each function. So what I'm going to do to solve this problem is I'm first going to break up my problem into two different problems. I'm going to split up the numerator. This second problem is equivalent to the first problem. I've made this problem much easier now because each of these two functions does match something on my table. Let's look back at the table. The first function that we have matches line 11. We have an s in the numerator, and we have s squared plus a constant in the denominator. The second function matches line 10. We have a constant in the numerator, and we have s squared plus the square of that constant in the denominator. So we can use both lines 10 and 11 to solve our problem. We know that the inverse Laplace of this whole function is equal to the inverse Laplace of the first function plus the inverse Laplace of the second. So the first function matches line 11. And the second of our functions matches line 10. Let's look at one last example. Now that we've seen one example that requires applying the constant property of the inverse Laplace, and we've looked at an example that requires applying the addition property of inverse Laplace, let's look at an example that requires some mathematical algebra skills and also requires using our Laplace transform table and the two properties. For this example, let's take a look at the transfer function that we found in the lab about the mountain bike. That transfer function looked like this. Now remember that a transfer function is equal to the output over the input. Let's see if we can use the inverse Laplace to find the step response of this transfer function. The first thing we're going to do is multiply both sides of the equation by the input. Since the input is a step function, the input will be equal to 1 over s. To find the response theta to this step input, we have to take the inverse Laplace of this whole function. So the first thing we're going to do is to see if we can match something on the table with this function. And remember that what we're going to do is first try and match the denominator. This line, line 24, looks like it's a pretty good bet. It has a 1 over s here, and it also has an s squared plus an s term plus a constant term multiplied by that. So we want to see if the numerator matches. The numerator here is a constant squared, and it's equal to this constant over here. Our numerator does not match the numerator in the table. We have an s term and a constant term. Furthermore, our constant term doesn't right now equal the constant in the denominator. So we know we're going to need to do a little bit of algebra to get our function to match something that's in the table. And we might also have to apply some of the properties. Let's start by splitting up the function into two parts so that the numerator will match the line on the table. I'm going to write this down on the next line because I don't have quite enough space. But this is just the sum of two functions. Now, in the first term, the s here being multiplied by this function is going to cancel out with the s in the numerator. Let's see if this first term and this second term can both be matched to some line on the table. The first term no longer has a 1 over s, so it doesn't match line 24 anymore. However, if we scroll back up in the table, we see that line 22 does match the first term in our problem pretty closely. Not exactly yet. We're still going to do a little bit of algebraic manipulation. But the denominator matches in that it has an s squared term followed by an s term followed by a constant. What about the second term in our problem? The second term has a constant in the numerator, and it has an s squared, s, and constant term in the denominator, and it's multiplied by 1 over s. Let's try and match it to a line on the table. Here in line 24, we have a constant in the numerator, an s squared, s, and constant term in the denominator multiplied by 1 over s. So the second term matches almost exactly, but not quite yet, line 24. Let's see if we can do a little bit of manipulation of our two terms to get them to more closely match the terms in lines 22 and 24. The first thing we're going to need to do is to make sure that in the term that matches line 22, there is a constant of 1 in front of the s squared. Right now, our constant in front of s squared is mr2 squared. So let's change that. The way I'm going to get this constant to be equal to 1 is by multiplying the numerator and the denominator by 1 over mr2 squared. I'm going to keep my second term here also, and in my second term I also need to get rid of this constant in front of the s in order to get this to match the table. So I'm also going to divide the numerator and the denominator by mr2 squared for the second term. And it looks like I need the R1 here. I dropped that out. Okay, so this term up here is the one that we're trying to match to which row on the table. We're trying to get it to match to row 22 on the table. And this term down here with the 1 over s, we're going to match that term to line 24 on the table, which has this 1 over s term. So the last thing that we need to get to match is that in lines 22 and in line 24 of the table, the numerator constant is the same as the constant in the denominator. So we need to do a little bit of algebraic manipulation to get this constant in the top to match the constant in the bottom. And the way we're going to do that is by using the property of the Laplace that says that we can pull out a constant in front when taking the Laplace. So let's do this first term here first. I want to get the numerator to match the denominator constant. So I want to pull out some constant in front, and when I multiply that by the thing that I actually want to have in the numerator, I want to make sure that it gives me the numerator that I actually have. So what would be the value of a here? I'll solve for a. Alright, so if I would take this constant that I just found and I would multiply that by the numerator that I have, I would get this value. So I'll simplify a little bit here. The m's cancel out and the r2 squareds cancel out. And now what I have to take the Laplace or inverse Laplace transform of is the value of a times this term except that I've used this constant to get my numerator to match this term right here. So now I can easily find the inverse Laplace of this. We pull the constant out front, and now this term matches the term in my table. Let's go look at what that term is. It's this whole term here, where zeta and omega n are found from my term. What are the values of omega n and zeta in this equation? I can find them from matching this term to the table. So this term right here is omega n squared. And then 2 zeta omega n is the coefficient in front of s. And we could solve this for zeta, and then we would plug in omega n and zeta into this whole term. Now that's the inverse Laplace transform of the first term, this one right here. We still need to do the inverse Laplace of this term. So we're going to make that match line 24, because that's the one that has 1 over s in it. We need to make the numerator match the constant term. In this term, that's a lot easier because the only thing we're missing in the numerator is r1. So I'm going to take this whole term and copy it down here. We want to take the inverse Laplace of this term. Now, in order to get my numerator to match this term here, I can see that it would match if I had an r1, and then all I would have to do is multiply this times 1 over r1, and that's a constant, and that would get rid of this term that I multiplied up here. So the inverse Laplace of this whole term will be 1 over r1, the constant, and then it'll be this whole term here that matches with line 24. I'm not going to rewrite this whole line here in my answer, but I am going to show you what omega n and zeta would be, which we would plug in here to omega n and zeta. Omega n here, once again, is the square root of k r1 over m r2 squared, which leaves us with 2 zeta omega n being equal to this term. So we now have the inverse Laplace of both this term and the other term, our first term. And we know that if we just add these two inverse Laplace transforms together, that gives us the inverse Laplace of the whole term. Which, if you remember, was this term here. Once we have these equations that represent the inverse Laplace, we can use these equations directly to create a plot of the time response. In lab, we're going to be seeing how to do that. Some inverse Laplace transforms are easy and other ones are hard. But whether it's an easy Laplace transform or a hard one, it's still true. The only things you need to know in order to do an inverse Laplace transform are the Laplace transform table, the Laplace transform properties, and some algebra skills to manipulate the equation to match something in the Laplace transform table using the two properties.